Welcome students, welcome to the next session of Strength of Materials 1. So in the previous class we have completed different loading combinations on cantilever beams and also on the simply supported beams, right? Where we have observed the application of point loads and also UDLs and also uniformly varying loads. And we have observed some combination of loads. There we have generated shear force and bending moment diagrams, right? So now we are going into the next concept. Before that we are going into our basic sign convention explanation. When we are observing any force about a section on the left side, if it is going upwards, we are considering as the positive shear force about that section. When any force on the right side direction is going downwards, will be considered as positive. Similarly, in the reverse condition, when any force on the left side is going downwards or any force on the right side of the section is moving in the upward direction, those forces will be considered as negative. So this is the sign convention for shear force. And also for the bending moment, we are having a condition called as sagging type moment and hogging type moment. So about a section, when you observe this type of moment application or this type of moment application, simply a overall convexity at the upwards, that can be indicated as the hogging type moment, and a overall concavity in the top or the sagging type condition can be indicated as the positive bending moment. So in this way we are giving the sign conventions for the positive moment and negative bending moment. Now we are going into the next type of beams. So in the first class itself we have explained the different types of beams based on the combination of the supports. When we are considering one end fixed and other end free, those type of beams we named them as cantilever type beams. And when we observe a hinge one end and the roller at the other end, this type of combination is giving the output of simply supported beam. Now we are going into the basic simply supported beam, but after crossing that support there is an extra portion, overhanging portion. So such a type of beams can be called as overhanging type beams. Okay. So firstly we are going into the basic definition. If the end portion of a beam is extended beyond the support, such type of beams are known as overhanging beams. So here you can observe the simply supported portion and an overhanging portion which is extending beyond the support. Even also on the left side also there can be expansion. Okay, overhanging portion. Okay, so these type of beams or a beam with like this condition. This is also overhanging. This is also overhanging. These also can be called as overhanging beams. Just our motto is a main simply supported portion and an extension of the overhang over the support. Only it should hang. It shouldn't have any support at the end. Only it should hang. Okay. So such type of beams we are calling as overhanging type beams. After that we need to know one more definition, that is point of counterflexure. Okay. So in our shear force and bending moment diagrams we have mentioned one point. When the shear force is becoming equal to 0 or the shear force is changing its sign, at that point the bending moment will be maximum. That is a condition of maximum bending moment. Okay. You can leave it aside. Now, when any other point is having bending moment changing its sign or bending moment is equal to 0, that point can be called as point of counterflexure. SF0 point has no name. Only SF is equal to 0 will cause maximum bending moment. That is the condition. Now, bending moment is equal to 0 or bending moment is changing its sign. That point where the bending moment is changing its sign, the point has a name, that is point of counterflexure. Okay, so the point where the bending moment is 0 or changing its sign. So when the bending moment diagram is having a shape like this, maybe at some point the bending moment is changing its sign, that point can be indicated as the point of counterflexure. In the next conditions we will observe this point of counterflexures and we need to locate those points also. Like where we have located, where is the position of zero shear force, like that. Here also they will ask where is the location of point of counterflexure. Okay, so that location we should have to calculate. Now I am going into a numerical for getting the complete understanding of the overhanging beams and generating shear force and bending moment diagrams. Simply draw SFD and BMD for a overhanging beam carrying a UDL of 2 kN per meter over entire length as shown in the figure. Also, locate the point of counterflexion. So, as shown in the figure, we are having a overhanging beam with support A and support B are at 4 meter apart and B to C is 2 meter apart, and it is being subjected to a UDL of 2 kN per meter. So, this is the overall loading condition we are observing. Simply, just when we observe a simply supported beam, how we will analyze, as the basic steps only will continue for the overhanging beam also. So, when you observe overhanging beam, you should have to get the remembrance of simply supported beam. How we are dealing? What is the first step to deal the simply supported beams? The first step is calculation of the support reactions. Here also the same thing, calculation of support reactions. So, firstly we are going with the calculation of support reactions. How we will calculate those? I am indicating them as vertical reaction at A as RA, vertical reaction at B as RB. When we are using the vertical equilibrium condition, summation of all the upward forces is equal to summation of all the downward forces. So, RA plus RB is equal to total downward load on the whole beam. RA plus RB is equal to total downward load on the whole beam, not only up to AB. Okay. So, as this is the whole beam, then RA plus RB, these two reactions will carry the total downward load acting. What is the total downward load acting? A UDL of intensity 2 kN per meter, which is spread over 6 meter length. So, 2 into 6. In this way, we are calculating RA plus RB is equal to 2 kN per meter intensity into 6 meter length. So, this is the 6 into 2, the total of 12 kN. Total upward force is equal to total downward force. Again, for the next equation, I am going into moment equilibrium. So, for the moment equilibrium, as we already know, 4 meter, 2 meter, RB, RA with an intensity 2 kN per meter. So, this is our overall beam structure. Now, I need to calculate moment about any point or any support point. Moment about any support. So, this is one of the support. I am taking moment about A. So, moment equilibrium, summation of all the moments about A. Okay. Now, moment about A is equal to sum of all the anti-clockwise forces is equal to sum of all the clockwise forces. So, about A, I can observe RB into 4. Any anti-clockwise force is there? No. Anti-clockwise force is RB only, is equal to, what is the load on the beam? That is 2 into 6. So, this total 2 into 6 of 12 kN load is acting in the clockwise direction. See here, it is making the body to go like this. So, it is generating a clockwise movement, and where it is acting, it is spread over 6 meter length. That's why it will act at 3 meter length from A. So, 2 into this 6. Intensity into length of UDL. This is the load value. This load is acting at 6 by 2. So, this total load is acting at a distance of 6 by 2 from support A. So, this is the condition. And after the cancellation, RB I have got as 9 kN, and in the top reaction we have got RA, so that RA is equal to 3 kN. After calculating the support reactions, what we need to do? We need to observe the spans, and then we need to go for the shearing force and bending moment diagram. Okay. So, for generating the shear force diagram, once you should have to observe the loading figure properly. Okay. So, for generating the shear force diagram, what we will do? We will observe the variation of load from section to section. Based on our observation, we will take one span. Okay. So, considering AB span, considering BC span, like that we will write, right? So, based on which thing? So, observing the loading frame or the loading figure, we will get the spans. See here, when I am taking any section at a distance x from A. So, what we need to do? So, we need to consider a section at a distance x from A. Now I am taking any section up to B. Okay, when we are considering any section up to B, so when we are considering any section in between A to B, what it is involving? That section is involving an upward reaction and an UDL of X length. Whatever is the section, when we are considering any section from A up to B. So up to B, when we consider any section line, it is involving a force of RA and also it is involving a UDL. Once we calculate this RA and RB, they will respond like the point loads. Okay? Once we consider RA and RB answers, they will respond like a point load application. Like that only we are multiplying, right? So on this beam, in this direction, some value of load is acting. On this beam, in this direction, some value of load is acting. That is our motive. Once it is RA, RB, nothing to us. Okay? Once RA and RB were calculated, only the value is matter. Value and direction. Using these two things only we are writing shear force and bending moment diagram, right? So up to B, this is same. Once I cross the B, when we take any section line in between B and C, which is measured from A, what it is involving? It is involving RA, it is involving RB, and it is involving a UDL of X length. Then we consider any section between B and C, and that section is measured from A, and it is involving a force RA and a force RB, and also it is involving a UDL of X length up to the section line. So that's why we are observing two spans should be considered, because A to B span, one section equation, and in between B and C another section equation. Okay. So firstly, I am taking the this is our section line. In between A and B, at a distance x from A, we are considering the first section line. So, how it will be? Fx is equal to summation of left side upward RA and summation of minus left side downward 2 into x. Intensity into length of UDL. So, RA, as we already know, 3 and it is 2x. So, 3 minus 2x is the Fx equation for the step. So, in between A and B, the shear force equation will be followed by 3 minus 2x. As we have already mentioned, this is for A and B. So, at the corner A, at the corner B, what is the shear force we are calculating? So, now at A, which is x is equal to 0. So, 3 minus 2 times 0, which is equal to 3 kilonewton. And then at x is equal to 4, at the support B. So, 3 minus 2 into 4, which we have 3 minus 8, which is equal to minus 5 kilonewtons. So, in this way, we are completing the shearing force calculation at the support A and at the support B. So, this is 3 kilonewton and this is minus 5 kilonewton. And when we need to connect these two answers, what is the equation following? The equation following is 3 minus 2x. Simply a single degree straight line equation, because highest power of the equation is 1 only. If we are having any x square, x cube term, what is the highest power we are saying? That is the overall degree of the equation. Okay. Now, we are considering the next section in between B and C, which is being located at a distance x from A. So, the next section we are considering at a distance x from A, that is being located in between B and C. Now, the forces involved are RA, RB and UDL of X length. So, RA left side upward RA and left side upward RB minus 2 times x. So, which is equal to 3 plus 9 minus 2x. As we have already calculated RA and RB answers, RA is 3, RB is 9. So, 3 plus 9 minus 2 times the x, we have got this equation which is equal to 12 minus 2x. So, in between B and C, when we need to calculate the shear force at any point, this is the equation. And for that point, the location is measured with x answer. So, at beam between B and C may be at 0.5 meter between B and C. So 4.5 from A. So at a distance of 4.5 from A, what is the shear force? With this equation I can calculate. At a distance 5.5 from A, what is the shear force? Once it is crossing 4, so I need to use the equation for this. At a distance x is equal to 3.5 meters from A, what is the shear force? For that I need to use AB shear force equation. Okay? At any point in between that section, those equations will give the corresponding answers. So at B and at C I am calculating the shearing forces. So x is equal to 4. We have got fx is equal to, just now we have got 12 minus 2x as the equation. So 12 minus 2 into 4, which is equal to 12 minus 8, which is 4 kilonewton. And then 12 minus 2 into, which is equal to 0 kilonewton. So at the point B and at the point C, we have got these are the shear force values. Okay. Now the connecting point, the connecting equation between these two answers is a single degree straight line equation, which is 12 minus 2x. Just now we have got. So involving all these answers, I should have to generate a shear force diagram. Okay. So considering first FA we have got 3 and FB we have got minus 5. A, B and C 3 minus 5, which is 3 and the value is 5. And in the previous step 4 and 0. So at B positive 4, at C 0. Okay. Now connecting lines between these answers is, first one is also a single degree straight line equation. Second one is also a single degree straight line equation. Okay. So here in between A and B, I can observe one special point where the shear force is becoming equal to 0. That point I need to look at, because that point will give me the position for maximum bending moment. So I am writing positive, negative and above the baseline positive, and this point is the, and the picture is a whole shear force diagram, and the point is 0 shear force, where it is happening in between A and B. So the equation between A and B, what is the shear force equation between A and B, that we should have to make it equal to 0, and from that we can calculate x value. So somewhere in between A and B, the shear force is becoming equal to 0, equating the SF equation for AB equal to 0. So 3 minus 2x is equal to 0. There we have got x is equal to 1.5 meter. So what it is, x is equal to 1.5 meter indicate at a distance of 1.5 meters from A, there will be shear force is equal to 0. So this is the explanation for the position. This is very, very important. Understanding of the problem or understanding of this step is involved in this line only. Okay. At a distance of 1.5 meter from here, we should have to consider, there is an observation of shear force is equal to 0. Now, then we are going for the complete picture, the original loading figure we are drawing, and then with the projection lines I have indicated A, B, C points, and then at A we have got positive 3, at B we have got minus 5, and at B in the next span. So starting from the baseline I am indicating 4 positive, and at C that is 0. Connecting two spans, there is a straight line equation only. One is a 3 minus 2x and one is 12 minus 2x. So in this way we have got this equation, and then there is a point with the 0 shear force that we have indicated as 1.5 meter in the shear force diagram. So after completing this part, we need to go into the bending moment diagram generation. So again the same thing, consideration of the spans will not change. Once the shear force diagram is clear for the spans, same for the bending moment diagram also, the same spans will continue. Okay. So the bending moment diagram. Firstly we are considering a section in between A and B, and which is being located at a distance x from A. And the corresponding mx equation is equal to, what is the corresponding mx equation? RA into x. Once the value is calculated, that is just RA, the corresponding answer. So it is the force acting in this direction, so positive RA into x. And on the left side there is a UDL of excellence. So minus 2 times x because it is giving the hogging type movement onto the beam. Only that force you should have to observe. What is this force doing to the load? So that force is causing like this. Leave it. Next, what is this force doing to the beam? That is causing like this. So negative. So 2 into x is the load value and which is acting at a distance x by 2. So the whole length of UDL is x and from the center there is the perpendicular distance. So that perpendicular distance is x by 2. As we already know, this is 3x minus x square. So in this way we have calculated mx answer 3x minus x square for the span between A and B. So for the section between A and B, in this span the mx equation is 3x minus x square. As we have got this equation, we can calculate MA and MB. And also we need to calculate bending moment at a point where the shear force is equal to 0 in this span. Okay. So bending moment diagram generation, further we should have to know bending moment at A, bending moment at B, and also bending moment at the shear force is equal to 0 point. Okay. As the equation for this is 3x minus x square. So 3 minus 0 square, we have got 0 kilonewton meter at the support A. And then at x is equal to 4 meter, 3 into 4 minus 4 square, 12 minus 16, which is minus 4 kilonewton meter. So in this way we have got the next bending moment at the point B. So as minus 4 kilonewton meter. In between these two, there is a point with a maximum bending moment. That answer, that is at shear force is equal to 0 point. At shear force is equal to 0 point. That point is at x is equal to 1.5 meters. And the corresponding moment will be the maximum bending moment. That's why I am indicating M maximum. So which is equal to 3 into 1.5 minus 1.5 whole square. And there we have got the answer as 2.25 kilonewton meter. 0 minus 4. In between these two, we have got a 2.25 value. See here, even though the 4 is a bigger value, but it is a negative. That's why maximum moment, even it is having a lesser value, but it is a positive moment. That's why maximum bending moment acting on this is indicated like this. Okay, ma'am? Now, considering the next equation. Where the next equation or the next section is being located? That is being located in between B and C. Again, measured from A distance. So, at a distance x, measured from A, that section is being located in between B and C. The corresponding mx equation we have got as mx is equal to plus RA times x, plus RA times x, and also plus RB times, what is the perpendicular distance between RB and the section line? As the whole is x, this remaining is 4. This leftover perpendicular distance is x minus 4. And also we are having the UDL. So UDL of x length is there. So intensity of the UDL and length of the UDL 2x, and it is acting at x by 2 from the section line, and it is giving the negative moment. So the complete, even it is crossing B point, there is no need of variation because the same UDL is spread over the complete length. So the same UDL we are writing everywhere. That's why the same UDL's answer only I am writing UDL intensity, length of the UDL into perpendicular distance from the load acting point to the section line. Okay. So RB we have got it is 3 into x, and RA is 3, RB is 9 into x minus 4. As after the cancellation we have got minus x square. So mx equation for the base span is 3x minus 9 into x minus 4 and minus x square. Okay. Now, as we have got this mx equation, again we need to calculate the bending moment at B and bending moment at C. So the calculation of bending moment at B and C, simply for the reference I have indicated the same mx equation. Just now we have got 3x minus 9 into x minus 4 minus x square. So from this condition, into 4 minus 9 into plus 9 into 4 minus 4 minus 4 square. So which is equal to 12 minus 16, and we have got it as minus 4 value only. So so 3 into 4 distance as it is equal to minus 4 kilonewton meter. So which is minus 4 kilonewton meter. And then bending moment at C. So 3 into 6 plus 9 into 6 minus 4. The generation of this equation was correct. 3x plus 9 into x minus 4. Both are generating in the sagging direction only. About the section line, these two forces are generating sagging. The UDL is generating hogging. This condition was okay. And the corresponding answers, we have got 3 into x plus 9 into x minus 4 minus x square. As it is correct. So we have got minus 4 kilonewton meter. Okay. And minus 6 square. So in this way, this is the 18 plus 9 2s are 18 minus 36, which we have got as 0 bending moment. 18 plus 18 is 36 minus 36, which is equal to 0 bending moment at the complete free end point of the overhang, that is C. So in the previous step, we have calculated bending moment at A, bending moment at B, and in between at SF is equal to 0 point also we have got a bending moment. Now we are going into generating bending moment diagram. So the first steps answer are taking RA, so MA is equal to 0 and MB is equal to minus 4. And in between at 1.5 I should have to give on 2.25. Okay, for that I am indicating the original loading figure also for the reference. So the original loading condition I am indicating with UDL, and with the projection lines we are indicating the next line 0 to minus 4, and in between these two at a 1.5 meter distance we have got 2.25, and connecting these 3 points, the equation I have got is a second degree parabolic equation. You can observe here also second degree parabolic equation connecting A, B and in between points. So 0, minus 4 and 2.25. I am connecting with a free hand curve. So with a free hand curve we are connecting. Simply connecting all these 3 points without using any skill. So connecting all these 3 points. And then at B I have got minus 4 and at C I have got as 0 answer. So that is minus 4 and to 0. So connecting these two, again we are using a smooth curve because the corresponding equation is again a second degree equation. This is a single degree, this is single degree, but the overall equation degree is highest of the x. So highest power of this x is 2. So second degree parabolic equation we are indicating as this shape. Now at A location, at B location, this is the B location, and at C location. In between A and B, I have got a maximum bending moment, and also in between A and B, I have got a point with 0 bending moment, as it is our bending moment diagram. At a point, the bending moment has changed its sign from positive to negative or negative to positive. In this way, I have got this point, and that point I can indicate as the point of counterflexion. In between A and B, I have got a point where the bending moment is changing its sign. So this is our point of counterflexure. So this point of counterflexion, how I can calculate? Like shear force is equal to 0. Here also I can calculate bending moment is equal to 0 in the EB equation. So using our equation AB, I can calculate the corresponding point of counterflexion. So in between A and B, the bending moment is changing its sign. It means in between A and B, the point of counterflexion is there with bending moment is equal to 0. So mx equation for the AB span is equated to 0. 3x minus x square is equal to 0, where I have got either. So when, as you already know, when the multiplication of A into B is equal to 0, what you can say? Either A is equal to 0 or B is equal to 0. Both A and B also can be 0. Okay, so A is equal to 0, B is equal to 0, or A or B. In this condition only, multiplication of these two, taking x is equal to 0 or x is equal to 3. So in this way, what do you mean by x is equal to 0? x is equal to 0 is indicating support A, as we are measuring from A point. So x is equal to 0 means at A location. So at A location it is saying bending moment is equal to 0. Yes, I already know. At A I have got 0 bending moment only. So the next equation will be the answer, that is the point of counterflexure, that is x is equal to 3 meters. So AB span is for 4 meters and at a distance of x is equal to 3 meters I have got the point of counterflexure. See here, at x is equal to 3 meters the bending moment is changing its sign. That means at 3 meters from A the bending moment is changing and that is the location for point of counterflexure. Okay, now the whole picture if we indicate it will look like this. So from the original loading figure indicating RA and RP, there we have calculated the shear force diagram. There I have got 0 shear force, and then from that 0 shear force and indicating the MX equation for AB and BC, indicating maximum bending moment and connecting all these points with a smooth curve the second degree parabolic equation. And also we have got a point of counterflexure. That point of counterflexure is at a distance of 3 meters from support A. So this 0 shear force point is I have got at 1.5 meter and this point of counterflexure I have got as 3 meters from A, as 0, 2.25 and in the negative -4, and in the next span -4 and 0. So in this way the connectivity of the bending moment diagram was completed. So in this way we are completing a shear force and bending moment diagram for a overhanging beam. Okay. Now I am going into the next loading condition. There I have observed another overhanging beam also by the application of point loads. See here, a beam of length 12 meters simply supported at the two supports which are 8 meters apart with an overhanging of 2 meters on each side as shown in the figure. The beam carries a concentrated load of 1000 newtons at each end. Draw shear force and bending moment diagram. So only we are observing or generating the loading figure. After that we are going into the conclusion of the shear force and bending moment diagram. So a beam of 12 meter length is there and it is being simply supported at the 2, but those two simply supports are at 8 meter apart. Beam length is 12 meters but the supports are at 8 meter apart and with an overhanging of 2 meters on each side. So this is the indication they have given, and also on each side, and the beam is carrying two concentrated loads at the free end of the overhang there 1000 newtons and also here. So as we have completed the original picture for the loading, I can go into the calculation of the support reactions, as our overhanging beams also will be the pattern of the simply supported beams only. Simply supported beam with overhanging portion. So analysis will start with the support reactions only. So I am calculating the support reactions. How we will calculate? Indicating RA and RB as the support reactions, and using vertical equilibrium and using moment equilibrium we can calculate RA and RB. So RA plus RB is equal to total downward load. Sorry. Total downward load 1000 plus 1000, because when we are considering two upward forces, the total downward forces acting are these two answers. Okay, in this way we are connecting, and we have got the total downward load is equal to total upward forces. And then already we have said we need to consider the moment about any support. Okay, we need to consider moment about any support. Other than that, if we consider any other point, two unknowns will be there in the same equation. If I am considering moment about A, what I can do? When we consider moment about A, what it will do? At that A, RA will not be considered because there is no perpendicular distance. So RA will be eliminated in the equation itself. So it is involving RB, and with the equation I can directly calculate RB only. So I am considering moment about A. Now see here, if you want you can write here itself. So about A, it is involving RB. About A, how much it is distant? As I have mentioned already, 8. So 8 in the anti-clockwise direction is equal to, we are having 1000 Newton in the clockwise direction, which is at a distance of 10 meter from A, and also we are having another load 1000 Newtons. Observe here about this point. About this point A, this 1000 is generating an anti-clockwise type moment. So about this point A, this 1000 force that is generating clockwise movement, but this is generating anti-clockwise movement. So summation of anti-clockwise movements we should have to indicate with 1000 into 2 meter. Sum of all the anti-clockwise movements is equal to summation of all the clockwise movements. In this way we will calculate RB answer. So 1000 into 2 plus RB into 8 is equal to 1000 into 10. So with this analysis, after eliminating the term, I have got RB as 1000 newtons and also RA as 1000 newtons. Without doing all these things also, as we have already mentioned, like when the loading is symmetrical about the center, when we are observing complete length of the beam is there and I am indicating the center line. About the center line, the complete left structure, the complete right structure are symmetrical. The RA and RB will be equal and it is equal to half of the total load. As the total load is 2000, so RA and RB will take total by 2. So in this way also we can write, if the loading is unsymmetrical or the shape is unsymmetrical, the pattern we go with is calculation with respect to the vertical equilibrium and moment equilibrium. Okay. In the next class, we will go into generation of shear force and bend moment diagram for this overhanging beam.